Just wait for a few people to settle down. All right, good morning, everyone. Welcome to Wednesday session. And to start off, we have Ian Moult telling us about energy correlators.
Perfect. So thank you very much to the organizers for putting on this great workshop and for giving me the opportunity to speak and to visit Taiwan. So today I'm going to try and give an overview of some recent progress in a program to try and connect certain ideas in formal theory, namely what goes under the name of detector operators or energy correlators, with real-world collider physics. And so I'm going to try and keep this at a pretty broad overview and just trying to kind of highlight some of the work that's been going on. And I also want to really highlight the connection with experiment, which has really been kind of developing the last year or so. And there's been a lot of more interplay between experiment and theory in a way that I actually think is really interesting. And so along with this talk, there was Kai's talk yesterday, who went into more detail on the kind of perturbative calculations. And then right after this talk, there'll be a talk by Chuan Han, who will go into it in a bit more detail from the CFT and light rate operator side. And so hopefully together, that will kind of give a picture of the work that is going on in this area. And I should also say, so I'll focus mostly on the case of QCD or collider physics. But since this is QCD meets gravity, this is good motivation to try and actually compute some of these observables in gravity. And so in the last little bit of the talk, I'll try and describe why that's interesting and then show some very preliminary results that we just put out yesterday of computing some of these detector correlators and energy correlators in particular in perturbative quantum gravity. Okay. So when you think of collider physics, what you typically kind of implicitly think of are exclusive scattering processes. So for example, S-matrix elements. And so this is an area where there's been tremendous progress in the last several decades. And so we now have a huge amount of theoretical data. So we understand very well the kind of analytic structure of exclusive scattering amplitudes. We have a huge wealth of multi-loop perturbative data for the last 20 or so years. And there's now, as was described yesterday, increasingly fancy ways of computing this, and even recently, non-perturbative understanding, which allows us to perform, for example, the S-matrix bootstrap in non-perturbative regimes. And so there's a very kind of practical outcome of this for experiments, namely the ability to accurately describe very complicated scattering processes in both the standard model and gravity. So at very high energies, we can work in perturbation theory, and so the details of this don't matter, but one can predict very complicated final states of the LHC to very high perturbative orders. And so this has been extraordinarily successful. And then at lower energies, more recently one has the S-matrix bootstrap. Again, the details of this plot don't matter, but one is able to actually start by combining effective field theories and properties of the S-matrix, actually get out non-perturbative information about low energy hadronic scattering. And so this has been overall very, very successful, although of course there's more to learn. But there's a very complementary regime at colliders, which is the regime of high multiplicity. And so of course, the reason why you get this physically in the real world, for example in QCD, is because the energy of your collisions is much, much bigger than the kind of mass scale of particles in your theory. And so when you collide things, for example, at TeV scales, you get these many, many, many particles coming out, or if you go to something like heavy ion collisions, you get thousands of particles coming out. And so in this case, it's no longer useful to talk about kind of an S-matrix, and instead what one wants to do is to move to some observables which are kind of like correlations in fluxes in infinity. So just like how you consider things in the CMB, you might want to measure, for example, multi-point correlation functions, for example, of energy fluxes coming off into your detector. And so another nice limit, which is kind of motivating for why you might want to study this kind of high multiplicity limit, or as a kind of thought experiment, is the case of conformal field theory. So there you don't have particle excitations, you just have some kind of mush coming off in your detectors, and you'd like to be able to understand what you could measure in, for example, a conformal collider. And so there was this very nice talk by Austin earlier in the week, where he described how one would like to move to a way of talking about things just on the kind of boundary. And so this was in the case of de Sitter, but even in flat space, so though we have a very good understanding of scattering amplitudes, we have actually quite a limited understanding of in-in style observables, particularly those on the boundary of, or on at null infinity. And so we do have one advantage in the flat space case, namely that we have a huge wealth of perturbative scattering amplitudes that we can use to just kind of brute force compute these observables. And so this has been used to great success to generate a lot of data, and Kai talked about some of the approaches to doing this. But so the intermediate steps for this are very complicated. For example, there's infrared divergences and many complications. And so one would like some way of kind of directly addressing these types of observables that live at null infinity that you can directly measure in collider physics experiments. And so we kind of like to learn to work directly within the space of observables which lives at null infinity. And so just to kind of reiterate the motivation for this, so the kind of very big picture idea is how can we characterize a theory using just this kind of asymptotic data or asymptotic fluxes which come off to infinity. And as I said, there's kind of two reasons for this, one theoretical and one phenomenological. And so on the theory side, there's kind of very basic questions remaining, kind of namely, what is the space of observables or detectors that we can measure at null infinity? And how are they related to, for example, local data of the field theory or conformal field theory that we normally talk about, for example, anomalous dimensions or OPE coefficients, and how can we use this to efficiently compute these observables? And then more generally, how do we kind of constrain theories in the absence of an S matrix and or local operators? So for example, if one has a CFT coupled to gravity, how do I perform some kind of S matrix or conformal bootstrap if I don't have a kind of observable? And so these kind of observables of fluxes coming off to infinity are the kind of natural space of observables to talk about in these theories, and one would like to kind of understand their properties. And so that's on the theory side. And so on the phenomenological side, the kind of reason for trying to understand these observables is in some sense much more obvious, right? Because this is directly what an experimentalist at a collider has to do. And so what we'd like to understand from that perspective is how do we kind of nicely relate these asymptotic measurements or measurements that one makes at infinity to parameters of the underlying theory, like couplings or transport coefficients or properties that we normally talk about the underlying microscopic theory. And also at a very kind of practical level, what we'd like to do is to understand how we can identify kind of universal features that can be computed to high precision. So when you take this very complicated collision here, it's very hard to actually do any first principles calculations and to really connect theory and data. So you have to choose quite carefully what you want to understand. And so to be able to do this, you really need to be able to isolate kind of universal features, for example, things like scaling dimensions that one can compute to very high precision and simultaneously measure very nicely in experiments. And so one of the things which is quite nice about this area is there's a huge wealth of collider data, which kind of provides us a very practical testing ground of these ideas and a kind of metric to understand if you're actually improving in your understanding. So if you come up with some nice new way of doing things, you can really test if it allows you to actually do something better at collider physics experiments. So there's kind of a very nice interplay of new theory ideas and actually trying to get new things out of colliders or get things out of colliders in a better way. Okay, so now what I want to go through is just kind of how we actually talk about these things in collider physics. And so the first thing we need to do is to understand what we want to actually try and measure, which will be nice to understand theoretically. And so I normally present this to a much more collider physics audience, where you have to convince them why it's useful to study correlators. And so this audience is very different, and so one is already kind of very convinced. And so the question that you might have instead is, why do people not measure correlation functions in collider physics? So in every picture of the CMB, people measure kind of correlation functions very nicely. And so you can ask, why doesn't one study, for example, non-Gaussianities or things like this in collider physics experiments? And so again, one of the reasons why it's very nice to do this just from a physics perspective is that by measuring correlation functions, you're really introducing a length scale. And so it allows you to very easily probe physics at that particular length scale. So when you have this plot here, you've kind of introduced a ruler. And so you know that the kind of physics dominating, for example, this peak is really associated to a particular physical scale in your theory. And so just experimentally, this is an extremely useful property to have. And so one would like to be able to kind of port over all this nice study of correlation functions that one has in both cosmology and condensed matter physics to the case of collider physics, so we can really kind of uniformize it and speak about it in this very nice language. And so the first thing we need to do is to understand what types of operators we would like to understand. So in these cases, one is always, or generally has a kind of fixed time slice, and you just have some operators at different positions. And so the first thing we need to do is to understand in collider physics is what actually is a detector operator in quantum field theory. And so on the experimental side, one has these very nice and impressive big detectors like this. And so to kind of make progress or to abstract this problem to quantum field theory, we kind of want to come up with the simplest little toy setup, which is kind of doing what one is actually, or mimicking what one is actually doing in this experiment here. And so for this, there's this very nice picture, which David Simmons-Duffin made, which I think kind of highlights the kind of theorist abstraction of what we'd like to do in these collider physics experiments. So namely, we have some hammer, which you can think of as kind of a local operator. And we use this to kind of perturb our system. So at the LHC, this is not exactly a hammer, but you can think about it, for an example, in an E plus E minus collider, and you really kind of excite the vacuum of the standard model, and then you have some fluxes which come off to infinity, and you measure them with some set of cameras. And so in your kind of Peskin and Schroeder, you learn how to decompose this hammer operator into a set of local operators, and these are what we use to kind of excite the vacuum. And so what we'd like to understand is how to work with kind of detector operators and how we can decompose, for example, actual real-world detectors into detector cell operators that we understand, for example, how to take their OPEs, what is their algebra, and kind of what is the rules for working with them. And so in some sense, the kind of big question is how to understand the space of well-defined detector operators in a given quantum field theory and how to kind of manipulate them. Because if we can do this, then we can really kind of make progress in understanding how we should think about real-world collider physics. And so in this talk, I'm going to mostly focus on the kind of simplest of these detector operators, which is a calorimeter cell or a detector operator that measures energy. And so Chuan Han will talk about a much more broad class of detector operators, and many of those can also be measured at the LHC. But for simplicity, I'm just going to stick with this kind of simplest operator, because this is kind of what people are often kind of thinking about. And so the very nice thing is that one can actually give a definition of a kind of idealized calorimeter cell or a camera operator that measures energy flux. And this is given here, and it's just kind of an Anik operator. And so what it is a null integral of the stress tensor just moved off to infinity. And so that's why it's kind of often drawn in this picture. You can think of it as either being local as on the kind of celestial sphere, or as a particular kind of, if you show in this Penrose diagram, it's kind of a null integral along one of these directions like this. So this is why one often draws kind of this picture here. And so more generally, as Chuan Han will talk about, you can put other fluxes or have much more generic operators which are kind of smeared along null infinity like this. But I'll just stick to this Anik operator. And so what one is really doing from the perspective of something like collider physics or jet substructure is essentially just measuring multi-point correlation functions of these objects. But the reason why this is nice is that now you can go off to your favorite, for example, conformal field theory or n equals 4 or something, and study the just generic structure of these correlation functions. So these have a lot of nice symmetries, and one can understand them, and then go back and try and use them in actual real-world collider physics. So you kind of successfully abstracted the problem to something that's a little bit more manageable than these very complicated LHC collisions. And so the reason why these observables are quite nice is they kind of take an intermediate position between amplitudes and correlation functions. So of course, the reason why we like scattering amplitudes for the LHC is they have kind of the asymptotic states going off to infinity. But of course, the problem is that they themselves are not IR finite, and you have to square them and get them into cross sections, and this is practically very difficult. On the other hand, if you're, for example, in a conformal field theory, you like correlation functions of local operators. So these you have very good control over. They're non-perturbably well-defined, and you have lots of nice ways of manipulating them. But of course, the problem with these is that they're just at some fixed positions. And so this is not what you want in a kind of scattering style experiment. And so at least for collider physics, the energy correlators kind of have the best of both worlds. Namely, they're kind of like a correlation function that's put at infinity. And so the other, at a very practical level, reason why this is very nice is it allows you to use techniques both from the amplitudes world, so for example, what was in Kai's talk, and from the CFT world in Chuan Han's talk, and kind of combine them to make very nice statements, which are actually for physical observables, which you can measure in real-world collider physics. But despite this kind of physical importance, they're much less explored compared to these other two. So of course, there's been a lot of recent work in trying to develop them, but compared to these, it's considerably less well developed, and so there's a lot of kind of low-hanging fruit or just basic properties to be figured out. And so I also just wanted to give, so though these are kind of have been picking up recently, they have a very long history, which is kind of intertwined with the history of QCD, and so I just wanted to highlight in one slide a little bit the history of these objects. And so they were actually introduced by Sturman 1 year after the discovery of asymptotic freedom, so this was extremely fast. And so he made the argument that if you take the kind of expectation value of these one-point functions, that this is something that should be calculable in perturbation theory. And so you could do kind of robust calculations, and so this is kind of the first collider physics observable in the modern sense. And so if you look at this paper, it has in 50 years, one citation, and so it's kind of completely overlooked. And so he did his, of course, later work with Weinberg, which got things going, but he actually wrote this down very quickly after the discovery of asymptotic freedom. And then in the kind of later 70s, this was generalized to kind of multi-point correlation functions of energy flow operators. and to kind of say that these are very useful observables for characterizing the final state in collider experiments in QCD, as I've said. And then this kind of lay dormant for 30 or so years, and then it was kind of resurrected in this important paper by Hoffman and Maldacena, where they kind of propose it more generally as an interesting observable just for probing the structure of quantum field theories. So just as I mentioned before, like the S matrix or correlation functions, that this is kind of an interesting general observable for learning properties of your theory. And so, for example, they had some nice conformal collider bounds and OPE coefficients, but this is kind of an interesting observable beyond just kind of practical QCD calculations. And so this had a big influence in getting this, or people thinking about this from the more formal perspective. And so then more recently, one has been trying to connect some of these developments back to real-world collider physics. And so another very important work was this, which I also just wanted to highlight, and this was kind of gone over in the talk by Kai, which had a big impact, is that this group here of Korchemsky and collaborators performed just an explicit perturbative calculation of these observables in n equals 4. And so often one thinks of scattering amplitudes as being kind of very beautiful structures. And so I think this paper was extremely influential in just showing that these observables or physical observables, which you can directly measure, can also have very nice perturbative structures reminiscent of amplitudes. And so Kai talked about this quite a bit yesterday, that once you have these multi-point correlation functions, they're functions of the kinematic variables on the sphere. And so you can get very nice kind of polylogarithmic structures in these kinematic variables, which are very reminiscent of what you get in scattering amplitudes. And so this is very nice because this is something which you can go out and directly measure. And so you can kind of bypass the taking amplitudes, squaring them, and just go directly for some very nice perturbative object or some object with a very nice structure, which is the kind of direct physical and final observable. And so these are kind of very influential in getting people interested in these types of observables. Okay, and so although I won't go into this in very much detail, I just wanted to briefly say a little bit about this kind of modern view. And so these energy correlators are just kind of one example of a detector operator that you can measure. So more generally, the modern view is that kind of in addition to kind of local line or surface operators, associated to every quantum field theory is some algebra of detector operators. And so these have some commutator structure and an operator product expansion. And so this is very nice because if you understand what the space of these detectors are, and so this is kind of what you could possibly measure, and you're actually able to use an OPE to study them and kind of manipulate them with this algebra, then you can just directly perform calculations just like you do for local operators in a CFT. And so, as I'll show later, in particular, this OPE is extremely efficient for actually understanding things in collider physics. And so if you understand this kind of space of detectors, it's a very efficient way of computing things in collider physics and trying to understand things from the collider physics perspective. And so the very nice thing, again, of these is they provide a kind of very clean map, or these correlation functions of various camera operators provide a kind of very clean map between the underlying quantum field theory and the physical observables, and so one can just go out and try and measure them directly, which is what we'll do. And so I just wanted to highlight, so this is kind of a nice, in the theory world, and so then the thing one should try and understand is, can this kind of theoretical idealization really work in this kind of very complicated and messy world of hadron colliders where things are extremely complicated, and you have to deal with kind of real world technicalities? And then the second thing is, can it actually provide new ways of understanding these collisions? So if you just do the same thing you could do before, that's not that exciting. And so one would like to use these to do kind of genuinely new things at collider physics. And so I'll hope to convince you that you can actually do this. And so before doing or showing that, I just wanted to emphasize two distinctions for people that were watching the talks earlier this week compared to the cosmology case. So there were very nice discussions. And so one big difference in collider physics is that we really control the initial state. So at the LHC, what this means is we can compute things in perturbation theory. So we have these beautiful scattering amplitudes, and these kind of set our initial perturbative state in which we evaluate these correlators. And so this we have very good control over. And then we can also just switch out what one collides. So this is something you can't do in cosmology. And so, for example, you can switch out and collide, for example, heavy ions and produce some quark gluon plasma, which produces these very good or very nice collisions here. And so here we really have control over the initial state and can tune it experimentally, and in certain cases control it very well perturbatively. And so that's one big difference. The other thing which I just wanted to mention, so there's this very nice formula presented in Enrico's talk. And so in this talk, I'm going to gloss over a lot of the details of how one does this in the real world collider experiments. So of course, I'll show kind of how one can compute these in perturbation theory, but in real-world collider experiments, you have kind of confinement and all this extra stuff going on. And there's actually a very close analogy with what happens in the cosmological correlator case. And so in particular, after kind of producing some state from some underlying scattering process, what one produces is some kind of perturbative structure which goes out, which you can detect. You can kind of imagine it at like the CMB level. You can measure these correlators on like perturbative quarks and gluons at very high energy. And so then ultimately there's some hadronization process where these turn into the hadrons which come into your detectors. And so there's regimes which you can go to, particularly at very high energies, where this is essentially a small or understood or kind of linear perturbation. And so I'll show cases where you can also image nicely the confinement, but for most of what I'm working on, or most of what I'll be showing in this talk, one is really in this regime where one can really interpret it as the kind of correlation measured essentially on perturbative quarks and gluons. And so this will be very nice because you can really see like spin correlations and all these kind of nice quantum properties of the quarks and gluons. And there's very small modifications going to this final non-perturbative structure. And so this really relies on having the extremely high energies of the LHC to make this possible. And so I'll mostly gloss over how we actually do this underlying step, but it's all actually in there. And you can think of it very much an analogy with these cases. Okay, so now what I want to do is kind of go over some of the recent progress in connecting with experiments. And so in the last year, one of the things that's been very exciting is there's been a lot of kind of direct measurements of these correlators across a huge range of experimental systems. And so I'll try and give just kind of an overview of the type of things one could do. And so I'll explain these plots in more detail as we go along. But just to kind of highlight at the beginning the types of things one could do. So at very high energies, one will be able to measure certain scaling exponents of these light ray operators or of these detector operators. And so these can be very extremely precisely measured. And so this is in a very perturbative regime where you can really compute them at the multi-loop order and do kind of precision tests. And so it really behaves essentially like a CFT. So then you can also measure them at lower energies. And so here you'll see a kind of, this is the transition due to confinement. And so you'll go from a nice scaling regime, you have some very sharp break, and then you'll go to essentially these free hadrons, which are coming out of your detector. And so this is a regime where the kind of corrections due to confinement are very nonlinear. And then finally, very more recently, one can also measure these in heavy ion experiment, and you'll also be able to directly see the modification due to the finite temperature or the kind of quark-gluon plasma effects. And so one can actually use this to learn about the underlying quark-gluon plasma. Okay, so the first and simplest thing which one can try and do with these is just to study the behavior at extremely high energies where one has perturbative control and study the two-point function. And so I'm not going to go into any details of these actual construction of the light ray operator. So it's actually quite, one can do it very concretely and in QCD, and Chuan Han will go through this hopefully in great detail in his talk. But so the very nice thing about these energy flow operators or these camera operators is they emit a form of operator product expansion. And so very schematically, it's kind of written here. But you can think of this as you can take two of these light ray operators and expand them just like you do for local operators. But now you expand them in the angle between the two detectors and onto some more general set of light ray operators, which again can be very explicitly constructed. I just kind of won't go through it here. But the very nice prediction of this is that at high energies, you predict just universal scaling, for example, of this two-point function as a function of the angle between the two detectors. And so in particular, because in a weakly coupled theory, you start off with operators of twist 2, if you go to very small angles inside jets, you'll just be dominated by the leading term in this OPE. And so it provides kind of a very practical way of actually trying to understand real-world, or this real-world measurement of this two-point function. And in particular, this is something which experiments can do, and they can directly measure it at very high energies at the LHC. And so if they go out and do this, and so this is a measurement at very high energies, so like 1500 GeV. So what they can measure is this two-point function as a function of the angular separation between the two detectors. And you can see that it exhibits this beautiful power law scaling shown here over kind of multiple orders of magnitude. So you get this kind of very nice scaling with some particular critical exponent, which I'll describe in a second, which is the exponent of the operator or the leading operator which appears in this OPE. And so I should emphasize that this is kind of real world data with no cleaning. And so it's kind of a very nice experimental realization of kind of asking a very simple question. You get a very nice, beautiful power law, which you can now then try and compute to very high orders. And I'll explain how to, or I'll show the calculation in a second. And so the other thing the other difference from cosmology is one can just keep doing these collisions, and so one has an extraordinary wealth of data. And so the experimentalists can actually go out and measure very high point correlation functions. And so this light ray OPE, you can then just use it to analyze these very high point correlation functions. And so one very nice prediction of the light ray OPE is that if you take some kind of endpoint function and scale it as a function of the overall angular size, it has an anomalous dimension which depends on the number of points. And so in particular, if you have a kind of j minus 1 point correlator, what you're probing is actually, or the leading operator is the twist 2 spin j operator in your theory. And so if you like this language of kind of Reggie trajectories, you're just kind of slicing across the different values of this capital J. And so if you normalize this j minus 1 point function to the 2 point function, what you get is kind of a scaling as a function of size, which is just a difference of anomalous dimensions. And so this is very nice because it kind of removes completely the classical piece. So it'd be kind of flat in a theory with no anomalous dimension, and you can just directly read off then by measuring this particular observable, the kind of spectrum of anomalous dimensions of the light ray operators in your theory. So just kind of by concretely measuring these endpoint functions, which is something that the experimentalists can do, you get direct access to the spectrum of anomalous dimensions. And so this is just a plot of this ratio here, all the way up to, so here I've switched to n instead of j, but up to 10-point correlation functions. And you can see that it actually, for each one, it has this beautiful kind of linear scaling, which is just associated with this difference of anomalous dimensions here. And so people have pushed this so you can do like 100-point correlation function and stuff, and it works very nicely because you just have so much data that you can really, or experimentalists can just go crazy with this. And so the very nice thing from a theory perspective is that you can actually compute this very precisely. And so this was done in collaboration with these excellent students, and so there's a lot going into really going from the theory side to actually making a full comparison with the data, which is being swept under the rug here. But you can actually compute these scaling anomalous dimensions to 3-loop order, so they're known very well in QCD. And so this is a comparison for different energies of the jets of the kind of theory prediction, which is shown in this blue, along with the data for this particular observable showing here. And so this is extremely nice because it provides kind of a very precise test of QCD, and you can see this very nice scaling behavior. And also, if you look closely, kind of one distinction from a conformal field theory is that as you go to higher and higher energies, the slope gets flatter and flatter. And so that's just the asymptotic freedom of QCD, that the anomalous dimensions become smaller and smaller as you go to the UV. And so, of course, this is just nice for illustrating that this OPE works and kind of understanding the spectrum of these operators. But you can also use it to actually extract the value of the coupling constant in QCD. So of course this anomalous exponent is just, at least in the perturbative regime, is just a function of the coupling. And so if you measure this slope very precisely, you can just back out the value of the coupling constant in QCD. And so even though this is kind of a very new technique inspired by these developments in conformal field theory, this was already actually used to perform the world's most precise measurement of the strong coupling constant from jet substructure. And so it's at about the kind of 4% level. And so this is currently beaten by certain kind of more inclusive or kind of traditional, so there's some certain other ways to do it, which the state of the art is about 1%. But this is kind of a very preliminary attempt to do this using this way. And so it can certainly be improved significantly using higher order ingredients. And so we're optimistic that this can actually be used to use this kind of light ray OPE to perform kind of a most precise extraction of the strong coupling constant and really take advantage of these very high energies at the LHC where you're in a very perturbative regime. And so I won't go into too much of the details, but I just want to flash a little bit about how this can be improved, and to really emphasize why this OPE approach kind of helps you at a kind of very practical level for understanding QCD calculations. So if you want to perform some calculation at the LHC of, let's say, like a 3-point function, which is what was used in this experiment, if you try and do this directly, this is extremely complicated. So essentially, you're not going to be able to do this at high perturbative orders. And so what this OPE does at a practical level is it essentially reduces a generic endpoint function to having to compute a 1-point function of some particular twist-2 operator at the LHC. And so for people that use a more kind of QCD language, what this is kind of an inclusive fragmentation or moments of inclusive fragmentation. And so one of the very nice things is that this is hard, but this is now manageable. And so in particular, there's a huge wealth of n and low scattering amplitudes, and so you can really kind of feed them in to perturbatively compute at very high orders this state, and then kind of interface this state-of-the-art calculation of the underlying state with this very nice scaling property of the of the detectors. And so at a very just kind of practical level, these kind of techniques for understanding these light rate operators have had a huge impact on how we do these calculations at the LHC. And so just to highlight that this is actually ongoing, so this is a more kind of technical plot, but what this is showing is just essentially characterizing this initial state or these one-point functions for a huge variety of different experimental conditions. And so one shouldn't really take away anything from this plot other than the fact that one can understand for a huge variety of experimental conditions, one can understand very precisely the kind of state that one is actually probing. And so this really relies on having these next leading order calculations of these multi-jet cross-sections. And so the hope is that this can be, or this will be combined shortly with the then OPE part to really make kind of very, very high precision calculations of the scaling behavior in the LHC environment. And so that's kind of the simplest thing one can do in terms of these perturbative correlators. And so one other thing which one could ask, and I mentioned a bit at the beginning, is that these correlation functions, or in QCD, has a confining scale, and so one should ask how that kind of appears in the detectors. And so, as one is well aware, QCD is not a conformal field theory, and so one should try and understand how this kind of evolution from high energy perturbative quarks and gluons to the actual hadrons which go into your detector, how this actually impacts the two-point function which you can measure experimentally. And so again, this is something which you have no understanding of. You have no understanding of theoretically, at least now, but one can just go out and directly measure this two-point function. And so far I've been showing you things in this regime over here, where you have this very nice scaling. So you have these non-integer exponents, which I discussed, and you have these non-trivial higher point correlations, which you can compute. And then at some scale, you just have a real abrupt transition, where you have some rearrangement of the degrees of freedom, and this is the confinement transition. And then on this side, what you see, and what is plotted here, is just an integer scaling, so it's just kind of a geometric scaling associated essentially with kind of random or non-interacting hadrons coming off into your detector. And you can compute, or you can measure higher point correlation functions, and they're all essentially uniform. And so although you can't actually calculate this, it gives a very kind of nice way of imaging the confinement transition, which hopefully at some point one will be able to learn a little bit more about, or at least extract something useful from. Okay, so one other thing which I wanted to flash very briefly, so there's been a lot of this progress at the LHC, but the LHC is a very complicated collider. And so this progress has actually motivated people to go back, so because we can switch out the initial state, there used to be E plus E minus colliders, and so fortunately all this data from the old E plus E minus colliders is actually saved. And so because they're very small, it's on like a thumb drive. And so you can actually go back and reanalyze the older data, in particular from LEP, and this ALEP experiment in this very clean E plus E minus setup. And so what we've done is we've convinced these people at MIT, so particularly this group of Yanji Li, to actually go back and measure these energy correlators using, in this very clean state, using old archived E plus E minus data. And so the reason one would like to do this is that what you're doing when you measure it in E plus E minus is you're really doing the simplest thing that you would like to do in a CFT, is you're really measuring this 4-point function, where here this operator is just the current which couples to QCD. So you're really doing this kind of hammer and camera experiment in the absolute simplest possible framework. And so the other nice thing which one can do is when you're doing an E plus E minus collider, you can really measure these energy correlators over the full kind of angular region over the sphere. And so when I show these things at the LHC, you have to do it in this small angular regime because you're inside jets. But here you can really just measure this like honest to goodness correlation function, which is the kind of absolute simplest possible object and the closest thing to connect to experiment. And so they can now go back and using kind of modern techniques for unfolding and stuff, they can use an extremely high precision or angular resolution measurement of this 2-point correlation function. And so it's shown here. So now this is over this full angular regime of these two correlators as a function on the sphere. And so this plot is a little bit confusing. And so on this side, what is plotted is the log of the angle. And on this side, it's the log of pi minus the angle. And so this is because you have kind of non-trivial asymptotic behavior as you either bring the detectors together, which is what I've discussed so far, or as you move them completely back to back. And so you see this very nice behavior where you're essentially probing the full kind of range of behaviors of QCD So far what I've described is this kind of light ray OPE or collinear behavior on this side, where you get this very nice scaling behavior, and then this transition to flat behavior of hadrons. And then on the other side, you have something which I won't describe, but it's described, or you can calculate in terms of a kind of Wilson line OPE, and it's probing the kind of physics of Wilson lines or high spin operators. And so again, on this side, you also have a regime which is dominated by some scaling of a different class of operators, and then you again have this transition to a free hadron regime. And so in gray is our calculations of this, and since they're actually starting to use very high precision components, so like 3 or 4 loops, and so we can actually describe this extremely precisely. And again, our hope is to be able to extract kind of properties of QCD directly from these calculations. And so this is also very, I think, interesting from a formal perspective of trying to understand how to, for example, bootstrap this object non-perturbatively, particularly in the confinement or in the confining regime. Okay. Now I want to move on and discuss a little bit what one can do with non-trivial states. And I think for time, I'll start moving a little bit faster. And so one of the nice things about these colliders at the LHC, as I said, is one can produce very interesting and non-trivial initial states, such as the quark gluon plasma. And so one can really tune this thing from these very low multiplicity collisions, for example, at the LHC, all the way up to these super crazy lead-lead collisions where you have this huge multiplicity. And so we'd like to understand what you can do, or why one would like to understand what one can learn both about light ray operators by studying them in these non-trivial states, but also what you can learn about the quark gluon plasma by having a nice kind of control over these operators. And so there's a kind of very nice analogy on the field theory side, and so whether or not this is a good analogy or whether or not this helps your understanding depends a little bit. But there's this very nice calculation of, again, by Korczynski and collaborators, of a kind of analog of this, where you can take very heavy sources in n equals 4. So you can take in particular these this operator shown here, these half BPS operators, and you can try and compute the multi-point correlator of these energy correlators in these very, very heavy states. And so essentially what this operator here does is it produces kind of K of these legs coming out back to back. And so it's kind of like a toy heavy ion collider. Of course, it's not really the same thing, but it gives some intuition. And they're actually able to compute weak coupling corrections to this, which is kind of like what you'd have in kind of, if you have a very heavy or kind of spray of particles in heavy ion, and it's having some jet going through it, which is perturbative. And then you can kind of perturbatively compute corrections to this. And in this limit, you can again do this operator product expansion. And what you find is this behavior, this kind of leading twist 2 behavior shown here. And then you get a twist 4 correction shown here, which is proportional to the expectation value of this particular light ray operator in this heavy state. And so this actually goes like 1 over this K. And so essentially what happens is this kind of flat or twist 4 correction starts to dominate as you put in more and more and more of this state. And so that kind of makes sense that as you kind of put in more and more and more of these particles, it just becomes essentially uniform. And so essentially what you'd expect is to have some regime at very small angles where this dominates, and then some transition to kind of a kind of flattish region which is dominated by higher twist operators. And so of course in the real world, you cannot just do this nice calculation where you have complete control, but you still have this light ray OPE, and so you can still organize it into a kind of twist 2 and twist 4, or matrix elements of twist 2 and twist 4 operators. And so very recently, the experimentalists have actually gone off and measured this. And so this is this 2-point correlation function, and it's a comparison of it in black in proton-proton collisions, and in blue in lead-lead collisions. And so you can see exactly as I kind of described in the previous plot, in this or in this previous motivation, that you have this regime in here. Sorry, this is hard. You have this regime in here where it has this nice scaling, and then at large angles, you kind of have this flattening. And so you can really directly see the impact of these twist 4 operators kind of kicking this thing up. And so this has really been measured as a function of what is referred to as the centrality, but essentially as a function of the size of the quark gluon plasma object which is produced. So you can kind of collide these at different, you can make them kind of hit harder and harder, and you can see that as you reduce from the kind of head-on collision shown up here to this kind of very peripheral collision shown down here, you kind of really reduce in this ratio between the results in proton-proton and in lead-lead, you kind of really reduce the impact of these higher twist operators. So it really is kind of coming from these, or the kind of effects of this plasma. Okay, so one thing which I think typically turns people off from studies of the quark gluon plasma is that when people do kind of theory calculations for this, they're almost always just using some models. And so they have these very complicated models, and they kind of feed them in. It's very hard to understand what is actually happening, and then one gets something out. And so, for example, people took their kind of models and tried to make predictions for this energy correlator, which I just described. And so it doesn't matter what they actually are, but these are some of the kind of predictions in these shown here. And so you can see that they kind of completely don't describe, even in the kind of qualitative shape, what is seen in these energy correlators. And so what we'd like to try and understand is if these new techniques, so in particular this light ray OPE, can actually be used to understand these more complicated at a quantitative level, these correlators in this heavy ion environment. And so again, at the lowest level, this actually turns out to be very simple because this OPE applies, so it's kind of a state-dependent, independent statement. And so one can just take the first two terms of the OPE, and so this is the term, or it's kind of the relative size of the expectation value of this twist4 operator and this twist2 operator, which will kind of give the impact of the QGP. And so we can't compute the expectation value of this twist4 operator in the QGP, but this is kind of one single number. And so what this predicts is the full scaling as a function of the angle and energies. And so you just need one number, which you can think of as just the expectation value of this thing in your particular QGP state. And so what you can actually do is to just take this, and if you use this, you can extract from one kind of measurement the value of this single number, and you can actually very nicely predict over a whole range of energies the behavior of these energy correlators in this QGP state. And so you're really able to actually understand using just one number kind of better than all these very nice or very complicated simulations. And it really shows that one can use this light ray OPE to try and actually understand what's going on in these very complicated states. And so there's a very nice as a kind of way of organizing one's thinking about these extremely complicated colliders, which were hard to get a control of before. And so our hope is that one can really use this also to probe the structure and, for example, to measure the spectrum of the anomalous dimensions of these higher twist operators, which would be very nice to be able to do. Okay, so now I've kind of talked a lot about what one can do with these 2-point correlators. And so now, obviously, things get more interesting as you go to higher point correlators. And so here I'll be a little bit more brief because Kai went through this in a lot of detail yesterday in her talk. And so I'll just kind of show how these higher point correlators can also be measured experimentally. And you can also really kind of connect at the level of even these very high point correlations directly between theory and data. Again, this is not something that needs to be convinced to this audience. But of course, it's very interesting to measure higher point correlation functions because they really start to probe the structure of the underlying interaction. And so, for example, just like how one does in the CMP, you kind of have these different templates for 3-point functions for different models of inflation. One would like to do this, for example, for different models of the quark gluon plasma. And then you could really measure 3-point functions and understand the underlying interactions in a case where you don't actually, or you currently can't compute what's going on. And so a very natural question is kind of what is the structure of these higher point functions of energy flux? And so surprisingly, even though these had been actually computed in inflation, they had never been computed in collider physics, with the exception of these very nice calculations of strong coupling by Hoffman and Maldacena. But here, because it's done strong coupling, it starts with being kind of completely uniform and then has small corrections. And of course, that's very different than what you'll have in a weak coupled calculation where you kind of have perturbative quarks. But as was discussed by Kai yesterday, we now have a huge wealth of very nice integration and amplitude techniques, which can just be kind of repurposed to perform these integrals and start computing these objects. And so there's kind of 2 different ways which one can do this. So the first is you can, if you have at your disposal a bunch of correlation functions of local operators, and so this is, for example, the case in n equals 4, you have these things very nicely, you can just take those local operators, you can apply this kind of integral or light transform, and smear them into these expectation values of energy correlation functions. And so this is something which has been used very nicely in n equals 4 to compute these things to very high orders. And so the other approach, which is what Kai discussed, is to just use kind of form factors which you integrate over the phase space. And so this is what has been used mostly in QCD, and in particular to compute these higher point correlation functions. And so as Kai discussed, one of the very nice things about these observables, so in general, if you compute them at all angles on the sphere, they're just some very complicated object which is also dependent on the underlying state. But you can take this multi-point OPE limit where you bring all of these detectors together, preserving just their cross ratios. And in this case, what happens is this essentially becomes independent of the state, and you also, at a practical level, just reduce it to these very nice projective integrals. And so most of what Kai discussed, and most of what's being explored for these, is really computing these at higher points in the collinear limits. And so fortunately, or what is very nice, is that this is exactly also the limit that you can measure inside higher jets of the LHC. So there you really bring them all together. And so this is why we can actually use all these very nice integrals for understanding these things in the collinear limit directly in the LHC setup. And so this is a very nice kind of coincidence that these are also easier to calculate. And so this is just a one-slide overview. Kai went through it in much more detail. But so at this point, one of the people have computed both the 3- and 4-point correlation functions directly in the collinear limit. And so they have very nice compact expressions in terms of polylogarithmic functions. So for example, this is the tree-level 3-point function in n equals 4 superyoung mills. And so it's just some expression in terms of single-valued polylogarithms. So there's been some very impressive recent work, which has actually gotten the integrand up to 11 points in n equals 4 superyoung mills. But this is very hard to actually integrate, and you start getting crazier things beyond 4 points. But I think there's a huge amount to be still explored just in their perturbative structure and as in trying to see some underlying simplicity in their calculation. But the very nice thing about these observables is that this is directly what you can actually measure. So these functions, instead of having to square them like amplitudes, you really just plot that function, and then this is actually what an experimentalist can go and measure in their detector, for example, at the LHC. And so this is a plot of, so these become a bit harder to understand, but this is a plot of this 3-point function, so technically it's normalized, so it's a non-Gaussianity. And this is actually in the real data shown here, and this is just a plot, it's essentially of the generalization of what I showed on the last slide, just a real-world QCD, so it just has some more polynomials around. And so you can see it has this, first of all, this quite good agreement, but also has this kind of nice structure. So over here, there's this kind of equilateral regime where you expect kind of contributions from like hard underlying operators, which are a bit suppressed. This is this kind of OPE regime, and so here when you've normalized it, which by the product of 2-point functions, which it factorizes into it, which is why it goes 1, and then over here is this kind of flattened regime shown up here. And so the very nice thing is you can actually kind of get control over these, you can directly measure them, and you're at sufficiently high energies that you're really in a regime where this is reflective of the underlying kind of perturbative 3-point function in terms of quark signals. And so just for people who have intuition for looking at these in cosmology, it's actually very easy to understand, for example, why it's enhanced in this kind of squeezed state. And so there's a nice paper by these people over here, where if you have some, so of course in the LHC, we're not coming out of the vacuum, we're of course shooting a particle in. And so it's really essentially just this propagator, which derives, or you can think of it as kind of an excited state, and that's why it's kind of dominated in this squeezed region. And so most of these behave essentially exactly the same, and same as if you have kind of like higher derivative operators, they would go into the equilateral region. And so these behave essentially exactly the same as, or a lot of the intuition from cosmological correlators can kind of be moved over, and one can nicely measure these objects of the LHC. And so one can actually,
Sorry, actually, maybe just one clarification of terminology for cosmologists.
Yeah.
Because squeezed is actually this triangle that has one of the external states.
Yeah, sorry, I pronounced it, yeah, sorry. So, yeah, this is squeezed and then this is flattened. Sorry, that was just a mistake on my,
We call this other one folded.
Folded, okay, we call it flattened. Okay, perfect, yeah. Okay, so this, folded limit, is...
Actually, squeeze is precisely where it's suppressed in your case. So.
Yeah, good. So, good. Because, so in this, so squeezed is this, where you have this, or where it just factorized in the product of 2, and so that's when you normalize it, it's suppressed in this, exactly. And then this, folded limit is enhanced because we have an excited state at the LHC, and we're not just producing these out of the vacuum. Exactly.
That's clear.
Perfect. Okay. And so at the LHC, they can just keep. So this is. So Kai yesterday showed this expression for the 4-point function, and so one can actually start just. So this is just plots of the n equals 4 version, just to kind of show what it. I'll show the data in a second. But these start to become these very complicated objects. And so these are also very hard to understand, but these plots are a bit harder to visualize. And so what one is doing in these plots is one is fixing, for example, in this 3 points. So you're fixing a triangle and you're kind of moving the 4th point around. So the full 4-point correlator is a higher dimensional object. And so in each of these, you kind of fix certain points and then move another one around, or in this middle one, you're kind of spinning these central 2 around while keeping the external ones fixed. And so these are just some kind of pretty pictures one can make. But the cool thing is the experimentalists can actually go out and directly measure it. And so what this is here is this is a plot. So this is like a 3, 4, 5 triangle that you put 3 of the detectors in, and then you move the 4th point around. And so this is kind of mapping out some projection of the 4-point correlator. And so you can actually just directly go into data and really kind of measure these things. At least for me, this is kind of very fun. You have like a real 4-point correlation function, which you can just move around. And you can test in these. You have all these nice spinning operators, OP limits, and kind of a lot of fun things. And so just to show one more kind of fun plot, in this one, what you're doing is you're fixing 2 of these detectors and then spinning the internal ones around. And so again, one can really kind of map out nicely. So this is an actual data, and so one can kind of nicely actually like really measure this with very high resolution and learn a lot about the structure of these higher point correlations. So what's been achieved on the experimental side in the last few years is really kind of remarkable that one can actually measure these objects. Okay. And so just before I move on, I just wanted to highlight, you could ask why one would actually want to, apart from fun, study these higher point correlation functions. Because really what it is testing is that we're able to just compute things in QCD. So of course in those previous plots we should just, and we are able to compute them. And so we'd now like to use them to understand some more complicated states. And so one fun thing which one can do, and so this is just using a simulation, but will hopefully be done in data soon, is that one can try measuring these higher point correlation functions in the quark gluon plasma. And so there, I showed earlier, if you just measure this 2-point function, you have these enhancements where it goes into this twist 4 regime at larger angles. And so what one would expect is that as you go into this regime, you should also see kind of interesting things happening in the 3-point function. And so what I'll show is as a function of this angular, or this slice shown here, the angular size, the ratio of the 3-point function. And we'll see that as, and this is between the quark gluon plasma and the vacuum. And so as you kind of step through, what happens is that low, or when you're in this kind of vacuum regime, you see nothing, there's just a completely flat ratio. And then as you move through and into this quark gluon plasma regime, you start seeing this huge enhancement in this equilateral regime. And again, this is really because you're kind of putting these higher twist operators in, or essentially you have operators that are not correlated with the collinear singularity. And so these are kind of enhancing the observable in this equilateral regime. So it's kind of like in cosmology when you put in some new operator. And so the hope is that one can really use this to actually understand properties of the quark gluon plasma. And so again, this is something which is extremely hard to compute from first principles. And so this is where another trick from this light ray OPE picture comes in, is that just like for normal correlation functions, one can really decompose these into what are referred to as celestial blocks. So these are just the kind of conformal blocks, but on the sphere. And so these are just some kind of functions of the angular coordinates. And so these are just like the kind of plots, if you just take a single block, what it looks like, again, as a function of these kind of triangle coordinates. And so the hope is that what one could do is kind of measure the results, for example, in heavy ion, and then kind of decompose it into these conformal blocks. And the hope would be that some of the kind of leading leading blocks would dominate, and you could actually try and understand some of the properties of the quark gluon plasma from this. And so the experimentals are trying to measure this now, and so the hope is that this will actually work out. Yeah. Oh, 5 points. Okay, perfect. Yeah, very good. Okay. That's and so that's, yeah, good timing is that, so hopefully I convinced you that at least on the collider physics side, this has been very nice interplay between theory and experiment. And so one thing which I thought was very nice is that David Simmons-Duffin gave this talk at Strings 2024. And so first of all, even though it's a string theory conference, he showed this actual data. And then one of the questions is how to measure general detector at collider. And so for the interplay between theory and experiment, this was very happy, and there's a lot of kind of back and forth and a lot of interesting questions that will really have an impact on better understanding collider physics. And so in the last 5 minutes, what I just wanted to talk about a little bit is some very recent work on trying to explore a little bit, motivated by this conference, understanding these energy correlators in gravity. And so this is work with Murat Kologlu, Enrico Herman, and then some recent help by Julio, which I'll show some very recent results. So first one could ask kind of why one would like to explore these detector operators in perturbative quantum gravity. And so at least for me, there's kind of 3 or 4 main reasons. So the first is that these are some well-defined asymptotic observables. And so in particular, as I mentioned before, if you're in a kind of CFT post-gravity, you don't have either the S matrix or local correlators, and so you just want some nice set of operators which you can understand. So the second reason, which is maybe more relevance to this audience, is that many of the observables which people are now starting to compute in classical gravity, such as waveforms and memories, so these can all be phrased as some form of detector operators. And so, of course, people can already compute these, but at least in the gauge theory case, understanding, for example, how to renormalize these detectors and how to kind of take their operator product expansions has been very clarifying for kind of setting up the kind of broad picture of these operators. So the hope is that that could also apply in some of these cases. So the other one, at least for me, is that in n equals 8, there's a huge wealth of very, very simple scattering amplitudes. And so we can hope that this leads to simple correlators. And so if one wants to understand just the kind of function space of these correlators, n equals 8 may be a very nice place to do it. And so finally, this detector OPE and all these questions about the normalization of the detectors, these are really IR questions because the detectors are at infinity, and so they should just be answerable within the kind of quantum or EFT regime of quantum gravity. So it's kind of a question that one can address, and so it'd just be interesting to understand, in particular, for example, the renormalization of these detectors in gravity. And so there was a very nice paper about, I don't know, a year or two ago by Gonzo and Pekraka, where they actually started kind of an investigation in a modern language of these observables, at least in classical gravity. So they wrote down a kind of nice definition of this ANIC operator. They then kind of studied the algebra of this ANIC operator and some other detectors which are generated by the boost and rotations, and they showed that very nicely these generate the kind of BMS algebra at infinity. They also observed, as it should, that in the classical case, so they computed them, they just factorize into one-point functions. And so here what we'll want to do is to actually compute the kind of quantum piece, where it doesn't factorize. And they also made a kind of very nice observation that, so in the gauge theory language, we often talk about kind of infrared safety, or this is what I mentioned of Sturman, that these can be computed in perturbation theory, and they kind of made an observation that this is kind of essentially implied by the BMS invariance of these operators. So you can kind of add in soft radiation, or kind of move them around, and the fact that these operators are invariant means that you can compute them in perturbation theory. And so what we'd like to do is now to extend this to the quantum case and to start computing these in perturbative quantum gravity. And so as I said before, so on the gauge theory side, we've really had a lot of progress just driven by just doing explicit calculations. So we have a lot of form factors and correlators, and a lot of understanding of the limits in the development of this library OPE has really just been driven by just brute force computing things and then trying to understand their structure. And so what we'd like to do in gravity is, before addressing these kind of more fancy questions, is to start computing things and just to start generate some data for the structure of these correlation functions. And so the simplest setup, which is what we'll consider here, is we're just going to consider kind of two scalars or two gravitons, it doesn't really matter, which annihilate into a whole bunch of gravitons, and then we measure the multi-point correlation function, here we'll restrict it to, going into the detector. And so one thing which is very convenient for us is that what this requires is the 2 to n squared and spin summed amplitude. So normally you could take the amplitude squared and sum over spins, but the kind of very nice thing is that particularly in supergravity, there's a huge wealth of these to very high loops. And so this is something that Julio can produce for us in one plane ride, and then we can actually start integrating and generate a kind of wealth of data. So fortunately, because these are already kind of spin summed and stuff, you really just cut them and then repurpose them for these particular integrals. And so this is very nice as a playground for exploring these structures. So all the kind of amplitudes are there, and one just needs to kind of start playing with integrating them. And so if you do this first in n equals 8 supergravity, so this is the expression. So again, it's very simple, just like the n equals 4 result for the 2-point correlation function. And so this is just the tree level for 2 annihilating into 2 gravitons going off into your detector. And so this is a function of the angle, so it's a bit more complicated now because you kind of have these beams. And so you have both this kind of azimuthal angle and then the separation between the 2 detectors. And so this is a plot of this 2-point correlation function as a function of the angular separation between the 2 detectors. And so if you remember when I showed it in E plus E minus, it had this nice like double structure like this, where you have both this singularity in the back-to-back limit and this collinear singularity. And so here, in gravity, you have this finite collinear limit, and so you can see this actually completely flat in the collinear limit, so you don't have a collinear divergence, but you have this kind of nice Sudakov limit in the back-to-back limit, which would be interesting to understand at higher orders. Sorry. I'll be very brief. So one can also compute this in pure general relativity. which we did with these people. So just like for the going from n equals 4 to QCD, essentially what happens is you just generate a whole bunch of rational functions which come as prefactors to the same functions, but again, it has a fairly manageable structure. And so one thing which is also just kind of fun is in the supersymmetric case, you have operators that in general have transverse spin and they mostly cancel. But in the pure gravity case, as you rotate this, you really see these kind of angular modulations, which are just due to the spin of the graviton. And so these excite kind of interesting transverse spin light ray operators, which have been investigated also in the CFT literature. And so finally, as a quick comment, which will hopefully be explained more in Chuan Han's talk, so we also computed more general detector-detector correlators. So in CFTs, what happens is these detectors are kind of made into, or they generalize local operators to being analytic in spin. And so one can write down detectors which measure more general quantities. So in particular, on the kind of leading Regge trajectory, what you're essentially measuring is energy to some power. And so one can compute this analytically as a function of the kind of spins of the operators involved. And you get this kind of nice expression shown here, which has this interesting analytic structure as a function of the spins. And so this will be very interesting for trying to explore the light ray operator product expansion and trying to understand the renormalization of detectors in gravity. And so this is just kind of a very preliminary investigation. There's a huge number of kind of interesting things that one should try and do. And so for time, I'll just skip over that. And so just to summarize, so in the last kind of year or two, there's been a lot of progress in understanding essentially these detector correlators in flat space. And so this is really having a big impact just at a practical level on understanding real-world colliders. And so in particular, the scaling and shape dependence of these multi-point correlators can be measured at the LHC. And so it's interesting to understand how these can be used both for understanding the standard model, but also for learning things about the light ray operators themselves. And there's a huge, I think, unexplored playground of understanding these detector operators in perturbative quantum gravity. And hopefully some of the same successes here can be used to understand certain questions there as well. And so, yeah, thank you, and sorry for going over time.
Any questions? Questions, yeah.
So you define these energy correlators by integrating over some null ray, right?
Yeah.
That usually assumes that like always in asymptotic flat space.
Yes. Yeah.
Is there a way of defining these objects in an asymptotic anti-de Sitter or de Sitter space where, I mean, in the Sitter, usually we consider like correlators in this equal time slice where you won't have any null ray, but anyway, I just wanted to know if people thought about that. Or...
Yeah, so there's some people I think that are currently thinking about this in the sitter, and I'll tell you more about it offline because I don't know if they want. Yeah, but there are ways of playing with it, and I think it's extremely interesting, and yeah, I can tell you more afterwards. Yeah.
Thanks.
So for the self-singularity at the back-to-back limit, do you get the virtual correction for the two-particle final state?
Yeah, so So when we did this, so we have not yet computed, so when we did this, what we did so far is to really compute it like in the bulk. So we didn't compute what are called like contact terms, like the delta of, in your case, like 1 minus z, or the delta of z. And so this is something like, probably this, yeah, just came out yesterday, so this is something we will and should do. And so that's important in particular for understanding the renormalization structure in this back-to-back limit. And so if you want to understand how, so at higher orders, this soft singularity will kind of exponentiate. And to understand that structure, it will come from understanding that detector. But it's kind of, it's a little bit different than in gauge. So in gauge theory, in this back-to-back limit, it's double logarithmic, so you have both a collinear and a soft singularity. And so in this case, because you don't have a collinear singularity in gravity, you just have a soft singularity. And so it's like a single logarithmic enhancement. But it can be studied in much the same way. And essentially by renormalizing the term you have discussed. And so that is, yeah, on the agenda to do. Yeah.
What kind of sources can you like put in the middle here? Like, can you put a black hole in some background field?
Yeah, I think that would be very interesting to try. Yeah, and Yeah, that would be, so one of the, yeah, so far we've only done this just kind of simple annihilation. And I think it'd be interesting exploring it in more general context. So one that would be very fun is to try and actually do this like in Hawking radiation, like multi-point correlations, but obviously a simpler thing, you can put anything in the middle and just like, if it's classical, it'll just be uncorrelated, but anything that you can compute corrections to, you could try. And I think it would be interesting to understand, yeah.